Hello, I'm Ikunom. I'm a software engineer at Line. This session will introduce you to Central Dogma, highly available version-controlled service configuration repository. Any non-trivial service needs to store its configuration somewhere safely. It could be a local file or remote file that is dynamically fetched while a server is working. Central Dogma is a repository service for textual configuration. JSON is primarily supported. Any text formats, including YML, XML, INI, and JSON are also supported. Central Dogma is highly available that ensures your service always read and write your configurations. All documents stored in Central Dogma are version controlled. You are able to query JSON with JSON path expression. When a configuration is changed, your service can receive the change immediately. You can set fine-grained access control to protect your repository from others. Additionally, you can mirror an external Git repository somewhere like GitHub, GitLab to Central Dogma. Among them, let's take a closer look at high availability. High availability is a system or component that remains operational for long periods of time without any interruption. It is generally measured as a percentage, with a 100% system meaning that service has experienced zero downtime. However, it is difficult to maintain a complex system that never fails. 90% and above of the rate of uptime is considered excellent performance. Many people think Facebook, YouTube, and Line Messenger will always be available. However, it is impossible to guarantee 100% uptime for any system. This is unavoidable even for big tech companies in Silicon Valley. Some of you may remember the Facebook failure that occurred in October 2021 lasted 5 hours. The main services of Meta, such as Facebook, Instagram, and WhatsApp, did not work. This has caused inconvenience to many people all over the world. If this failure occurred during typhoon, earthquake, or other natural disasters, it may lead to serious damage due to the destroyed communication. These unexpected disasters are inevitable, but there are some ways to minimize the failures. A single point in particular is easy to be a risk to a system. You should not feel at ease even though your system has been working well for a long time without any problems. One day suddenly, a disk could be broken. A network cable could be disconnected. A power supply could be unplugged. Otherwise, wrong code made by someone could lead to a failure. We call this single point of failure. Master-slave model is a traditional architecture to avoid single point of failure. This architecture consists of one master node and several slave nodes. MySQL database, Redis, and many well-known open-source software supports master-slave architecture. Data is copied one way from the master to slave. Client can perform write and read operations on the master node and can perform read operation on the slave node. It has a relatively simple architecture. However, there is one thing to note. As replication occurs one way from the master node to the slave node. If you write a change to the slave node, data inconsistency between master and slave will occur. In the master-slave structure, only one master can exist. It can be a single point of failure. What if there is a problem with the master node? All write operations should be stopped in case master has some problem. Consequently, clients would continue to fail the write requests. And the replication is also stopped. Although data could be read from the slaves, the service could end up with an outage. If the master has stopped, one of the slave nodes should be promoted to the master. The processing of promoting a slave to a master is quite complex. To promote a new master in case of failure, first of all, monitoring is important. You should keep observing the master's state and automatically determine whether the master is enabled. Next, we need to decide which of slaves that you are going to promote. Sometimes, one slave is used in order to reduce the complexity of selection of new master among several slaves. After the promotion has completed, which node should the client send write operations to? We should design how the new master information is delivered to the client. We may use one solution of load balancer, DNS, or service discovery. However, each method requires a fairly complex and sophisticated operation. Although we try to guarantee HA through this complicated promotion process, temporary suspension of service during promotion is inevitable in the multi-master structure. This time, let's take a look at the multi-master architecture. Central Dogma can establish replication using multi-master. In multi-master mode, all nodes in the cluster act as master. As we saw earlier, we can perform both write and read to master. Clients are able to send a write operation to any node in the cluster. Clients do not have to know which node is the master node. You can just distribute client requests through a load balancer or client-side load balancing. Another advantage of Multimaster is that we can evenly distribute the write load to the replicas. If one node goes down, the unavailable instance is just excluded from the ensemble of Multimaster, and the entire cluster continues to function. Clients will remove the broken master node from the target host through hash checking. There is no complex promotion in Multimaster architecture. Also, the write operation continues to work without any interruption. Previously, we've learned Multimaster architecture has only one master in a cluster. When the data is committed to the master, it is stored and the transaction for the request is completed. Speaking of Multimaster, write operations take place in a different distributed environment. Data is committed, one master node should be applied to the other master's nodes. When other master nodes successfully receive the new change, the transaction will be completed. For this, a master should forward replication logs to the other masters. To complete the change, a consensus algorithm such as wrapped is necessary. Consensus algorithm is out of scope of this presentation, so it is not covered in detail. Another problem is a concurrent modification. It happens when different masters try to modify the same data. Let's say a request tries to change A to B with master 1, and another request tries to change A to B with master 2 at the same time. It may cause a conflict. So now we need two features. First, it is a consensus mechanism to safely deliver replication logs to multiple master nodes. Second, we need to prevent concurrent modification for the same data. We didn't want to reinvent the wheel from scratch. Central Dogma implemented an optimized replication logic and distributed lock between multimasters on the top of Apache ZooKeeper and Apache Curator. Apache ZooKeeper is open source server for distributed coordination. Apache Curator provides a variety of recipes on the top of ZooKeeper, which Central Dogma needs. ZooKeeper is a server like Central Dogma, so we had to build a separate cluster. However, external component could be another single point of failure. It's not good for Central Dogma because Central Dogma should guarantee high availability. So Central Dogma decided to internally launch ZooKeeper by dynamically creating the configuration of ZooKeeper at runtime. Thanks to embedded ZooKeeper, Central Dogma is able to create a ZooKeeper server that shares the lifecycle of Central Dogma without external dependencies. The embedded ZooKeepers are creating an ensemble and ready to synchronize data as Central Dogma servers starting. We use ZooKeeper as a channel of replication rules as well. When a change is made, Central Dogma safely stores the change to the local storage first. When the write for local storage is completed, a replication log is created and saved in the G node of ZooKeeper. ZooKeeper delivers the new data to the other ZooKeeper nodes. If other master nodes has successfully received the replication logs, the write transaction will be complete. The delivered replication will be applied to the local storage or remote peer in the end. Let's talk about distributed logs. In order to avoid concurrent modification, a shared reentrant log provided by Apache Creator is used. We can control concurrency of different JVM by using the shared log. If master 1 acquires the log on A, and master 2 also tries to acquire the log on A, the permission for master 2 is not available. Master 2 needs to wait for the permission. When the change on the master 1 has finished, the log is released and the change on the master 2 starts. At this time, since the value of A has already been changed to the B, the change from A to C on master 2 will fail. The client will detect the failure due to the conflict and may retry to make a change after reading the new value. Multimaster servers does not solve all the problems. Servers of cluster are usually located in the same data center to minimize network latency. The data center can suffer a power outage or network disruption at any time. A consensus algorithm is a process used to achieve agreement on a single value among distributed processes or systems. Consensus is essential for safe replication. Therefore, the consensus should be maintained for the continuous replication. If more than half of clusters are broken, consensus is also broken. So the replication and write operation will stop. In the worst case, an entire dataset goes down. The read operation becomes impossible as well. Tolerance to the outage of a single data center is now considered essential for many online services. In fact, consensus slows down as the number of replicas increases. If we install 15 replicas on 3 different data centers, 8 votes or 15 replicas are required for the majority vote. The increased minimum required votes can slow down the overall replication speed, and it would take longer to acquire a distributed log, which are really bad for system performance. ZooKeeper provides a hierarchical quorum option. Each cluster is considered as a group that can form a hierarchy quorum. In this case, consensus completes if there are 2 votes from 3 groups. Each group requires 3 votes, and only 6 votes are needed to make a consensus for replication or loss. Additionally, since the instances in the same data centers are grouped, the cluster in the same group can communicate faster. A hierarchy quorum is more stable than single big quorum. Even if 7 replicas out of 15 are broken and only 6 replicas available, all operations of service can be performed. Client can access Central Dogmas located in a different data center and continue to write and read operations. The combination of hierarchy quorum and multi-master architecture makes the system resilient to a disaster. All data must be stored safely. There are many well-known open-source repositories such as MySQL and Redis and so on. But external storage can cause another single point of failure. Honestly, it's possible to set up HA for those systems and could remove single point of failure. However, it's still difficult to automatically failover by orchestrating external systems at the same time of failure. To reduce this complexity, Central Dogma implemented an internal storage and manages data itself. Central Dogma uses Git to create a durable local storage engine. JGit is a lightweight, poor Java library implementation of the Git version control system, including repository access routines, network protocol, and core version control algorithms. JGit is a relatively full-featured implementation of Git written in Java and is widely used in the Java community. Central Dogma internally uses JGit to create Git repositories. Thanks to JGit, you can see diffs and the authors of commits so that you can track the change of your data. In-memory storage engines such as Redis limit the size of the entire data to the size of RAM. But since Git stores data in the file system, is able to store data more than RAM. In Git, each commit has a hash value, which has no special meaning. Therefore, it's difficult to get the creation order of data from hash values. To overcome this, Central Dogma provides a simplified version of Git. Each hash value of commits is mapped to an integer revision. A new commit has a revision increased by 1 from the previous revision. Additionally, single branch is used to provide a linear history. We've seen several techniques used by Central Dogma to ensure high availability. Although we focused on HA, Central Dogma provides other useful features as well. An advanced query mechanism for JSON data is provided. You can query JSON data similar to SQL through JSON path. You can select specific fields from JSON data. It is also possible to filter values smaller than a specific value through a conditional statement. In addition, it provides various ways to query data, such as regular expression matching. Using JSPatch, you can express the operations of create, update, and delete structurally. You are able to delete a value in a specific path through remove operation, and add a new value to an existing value through add operation, update value with replace operation. When a service starts, the service may need configuration to initialize the application parameters or beans. While the service is running, the configuration should be dynamically changeable. For example, an API that limits the incoming requests for throttling should be updated by operators. The ratio of loadout or AV experiment need to be controlled based on users' feedback or machine learning results. Watch API is the most loved feature by users. Clients get notified or change immediately when new commit is pushed. A JSPath expression can be used to listen to uninteresting data of entire JSON. Currently, Java, Go, and Rust clients are available, and we are working on implementing Python client. Fine-grained access control is mandatory for enterprise-grade software. Central Dogma uses Apache Zero as an authentication layer that lets you integrate Central Dogma with your system's authentication system. Additionally, 4 roles are provided: administrator, owner, member, and guest. Permissions for read and write can be separately granted to the role. For example, owner can read and write. Member can only read, but guest cannot access it. Application token is useful for clients and REST API. You can access limited resource by including the application token to the header. Central Dogma is not only creates its own Git repository, but also mirrors an external Git repository. If you use the mirrored Git repository, you can make your change reviewed. This will prevent the configuration from being mistakenly changed with incorrect values. If the pull request is merged, Central Dogma automatically updates the changes. It makes the configuration in the external more queryable, watchable, and highly available through Central Dogma. You can also minimize network latency by locating Central Dogma in the same data center with your services. This is the Central Dogma architecture that brings all these features together.